We now take a look at one way that determinants can help us to solve linear systems. And this is a method or a rule that was discovered by British mathematician Cramer, right? In fact, he's the one that developed a lot of the theory of matrices that we almost take for granted today, right? And what I'm going to do is to kind of to give you an idea of where this rule comes from. Let's go back to where this course started, right? A linear system, and let's just look at the two equation, two variable case. But what I'm going to do is not write down a system where we have specific numbers for the coefficients, but instead we have like just placeholders. So consider the system. Let's say it is ax plus by equals, now since I have b over here, I'm going to call this u, and cx plus dy equals v, right? And just so that you're clear on this, let me write the matrix form of this system. Right, so here is the matrix form. So our variables are x, y. That makes the coefficient matrix the typical way we've been writing down our general 2 by 2 matrix, A, B, C, D. And then that means our variables will make up this column, this x, y column. And then the UV will make up another column for my constants, right? So here's the matrix form of this system. And what I'm going to do is just solve this system like we normally did. Let's say before we knew about all these, fancy things, right? So I want to eliminate, so let's start by trying to eliminate the y. So what I'm going to do is multiply the top equation by d and the bottom equation by b, right? So that gives me this new system, right? So here I'm just going back to the good old ways of basic algebra where you just look at coefficients and you try to, multiply stuff. Okay, so the stuff that we're going to multiply, we're going to take the first equation and multiply it by d. So I'll have a dx plus b dy is equal to du. And then multiply the bottom equation by b. So I'll have bcx and then plus b dy is equal to bv, right? So if I call this equation 1, and if I call this equation 2, and if I subtract 1 minus 2, then I'll eliminate the b dy terms, right? That was the whole idea of multiplying the top and the bottom by certain constants, right? That's one of the standard tricks. So if I do 1 minus 2, I'll have a dx minus bcx. The b dy terms will cancel out, and then I'll have a du minus bv. All right. So now if I want, remember our goal is to try to solve for x. So I can factor out an x here. And then that leaves me with, look at that, AD minus BC. Where have we seen that before? And then DU minus BV. So then, as long as the AD minus BC is not equal to 0, and again, we know what that means, right? So if AD minus BC is not equal to 0, then I can divide both sides by this quantity, and then I would have my solution for x. So it's going to look like du minus bv over ad minus bc, right? In fact, let me write this one more way. So I'm going to just to have everything kind of matched up perfectly, I'm going to switch these around and I'm going to put it as UD minus BV over AD minus BC. All right, so keep that formula in mind. Now, we want a similar formula for y, right? Because the solution isn't complete until I know what x and y are. Not just x, but both. Now, there are two ways we could do it. I could take this expression for x, plug it back into one of my original equations, and then solve for y, right? Which wouldn't be too bad. Or I could kind of go back here and do another kind of elimination process, and it probably will be a little bit messy if I do the latter, right? So let's say, so I'll keep it in this row again, or yeah, in this line. So if I want to eliminate the x now, so I'm going to multiply the top equation by c and the bottom equation by a, right? So if I multiply the top equation by c, I'm going to have ACX plus BCY minus, or sorry, is equal to CU. And then if I multiply the bottom equation by A, I'll have ACX plus ADY is equal to AV. And again, let me call this equation 3. Let me call this equation 4, and then do the same thing. Let's take 3 minus 4, so let's subtract. So 3 minus 4, what are we going to have? Well, so these terms will cancel out. I will have BC minus AD, so I'll have BC y minus a dy, and then I'll have cu minus av. So cu minus av. Now, if I want this to kind of come out similar to this, I would want this coefficient to be positive, and similarly, I would want this coefficient to be positive. So let's multiply this equation by -1. So then it becomes ADY minus BCY is equal to AV minus CU, right? So basically just changing the coefficients of all four terms. Now factor out the y, and notice we have the same AD, oh, not B, AD minus BC, and then over here, again, I don't have anything in common, so I'm just going to write it as AV minus CU, right? And then again, under the same assumption that AD minus BC is not equal to 0, then my y variable is equal to this expression, AV minus, I'll write this as UC over AD minus BC, right? So essentially what we've done is we've come up with these two formulas for the solution of any 2x2 system. And as long as the AD minus BC is not equal to 0, then we will get a unique solution. In fact, that's what we essentially proved that earlier using determinants, right? And speaking of determinants, so let me take this equation that we have for x. In the bottom, I can express that as a determinant. So I can express it as the determinant of, again, our typical 2x2 matrix. So it's AD and then minus BC. So then this would be your C, this would be your D. And then since something is very similar here, it's almost like I could set this up, this numerator, as another determinant. I could set it up as a determinant Since the D and the B are in the same position here, I could have my second column would be this, and then this would need to be a U, and then this would need to be a V, right? So it looks like we can express our unique value for y in terms of determinants, right? And then I can do the same thing. Well, the unique value for x can be expressed in terms of determinants, and I can do the same thing for y. So y, let me write that right below here. It has the exact same denominator, so I can use the exact same determinant here. Your A, B, C, D. The numerator is a little different though, but the A and the C are in the same position, so I can keep these as A's and C's, and then simply replace the B, or I should say the D, with V, so right here, and then the B with the letter U, right? So I'm basically taking what I know about the form of a determinant for a 2 by 2 matrix, and I'm setting up this answer in terms of determinants, and then I'm doing the same with this answer. Right? Now let me write the matrix, the system that I wrote down earlier for the matrix. So the matrix form of the system, we had A, B, C, D. We had our column with their variables x and y. And then we ended up, and then we had our column with our constants here, the u and v. So do you notice what goes in the denominator is the determinant of the coefficient matrix? And as long as that determinant is not zero, both of these expressions are well defined, right? So it looks like the determinant of the coefficient matrix goes in the denominator, both of them, right? And then if you look carefully in the numerator, it looks like the column here, right, that represents the coefficients of x, that column gets replaced by the column UV right here. So it's like you replace the AC column with the UV column, and you don't change anything at all with the BD column. And that is the numerator in the fraction for x. And similarly, look at the numerator for y. It looks like we took the y columns, right, the coefficients of y, and we replaced it again with our constant column uv, right, and we didn't change the AC. And Cramer realized this, and he realized that it's not just true for a 2 by 2 system, but in fact it's true for any n by n system. As long as the determinant of the coefficient matrix is not zero, then we can express the unique solution of the system using determinants, right? So let's state what the theorem says, and then we'll do a couple examples, right? So I wanted you to see where the sort of pattern comes from. You could do it with the larger matrices, but if you try to use this method, it gets very, very messy, right? So here's our theorem, and this is Cramer's rule. Right, and it says so, and it starts out with the most important of the hypotheses. Let A be an invertible matrix, right? And B be the column vector with the components. So B with I'll call it a column matrix or column vector. So a column matrix with n components or n entries, right? So A is n by n and B is n by 1. And let A sub I be the matrix obtained by replacing, the ith column of A with B, right? So again, that's kind of what we saw up there, where you replace one column by your column with the constants, right? So if our x column now, so basically I'm just writing down what my variables are, and again I'm using our standard variables for a linear system, x1, x2, dot dot xn, right? So is the unique solution, right? So, and we know it has to have a unique solution because our matrix is invertible. That's one of the things we proved earlier. So is the unique solution to the linear system, and again this is our form of writing our linear system, or ax equals b, where n is our n by n, x is a n by 1, and b is a n by 1. Then here is the punchline. So this is what Cramer figured out. He said the ith variable can be expressed as a certain fraction. And what is that fraction? It's the determinant of AI, so one of these new special matrices where I have a certain column replaced, and that determinant is divided by the determinant of the original coefficient matrix, A, right? And this is true for I going from 1 to n, right? So for I equals 1 to dot 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 n, right? And that's what Cramer says. So it's kind of a lengthy thing to state just because of the process that's involved. But when you see an example, you'll realize that, hey, this isn't so bad after all. And in many cases, 2 by 2, 3 by 3, once you're comfortable computing determinants, this is actually for relatively small n, this is not a bad way to go about solving. But it does require that your coefficient matrix be invertible. All right? So let's take an example, a 2 by 2 example to start. And we're going to use Cramer's rule to solve both of these systems. So our first one, let me just write it down. So let's say it's 2x plus 3y is equal to 2, and then negative 5x plus 7y is equal to 3. All right. So again, let's go ahead and write this in the matrix form. That way we identify, the columns and the coefficients and so forth. So the matrix form of this system looks like that. That's our coefficient matrix. And then in this case, we're just using x and y since there are only two variables. And then over here is my b column, my constant column. So there we go, right? So first, let's write down all the a's that we will need. So the coefficient matrix, that is the matrix 2, 3, negative 5, 7. A1 is where I replace the first column, so that's what this subscript is telling me. Replace the first column of A with my constant column here, 2, 3, right? So for this one, I'm going to take this and replace that column. and then that's going to be my a sub 1, right? So instead of writing 2, negative 5 as my first column, I'm going to write 2, 3. And then I don't change the second column, right? You're replacing one column for each, essentially for each matrix that you need, right? So 3, 7, all right? And then let's write down a sub 2. So that's where I'm now going to replace the second column. So again, if I use that, now that's going to replace that one. So the blue one, the blue process is what you do to form a sub 1, not a sub 2. So a sub 1 there. And then the green process is what you do to form a sub 2. So in that case, the first column stays the same, 2, negative 5. And then now my second column is 2, 3, right? And then Cramer says we need all three determinants, right? So let's write down the determinant of each. So the determinant of our original coefficient matrix is 14 minus negative 15, so that is 29. The determinant of A1, this one is 14 minus 9, so that's 5. And then the determinant of A2, that is 6 minus negative 10, so that is 16. And then I can write down what x is, right? So my first variable, or whatever variable comes or is represented by my first column here, that value, its unique value, is the determinant of A1 divided by the determinant of A. So this number divided by this number. So 5 over 29. And then my second variable y, well, y is its coefficients are in the second column. So that's the A2 matrix that we formed, and its unique value is the determinant of A2 divided by the determinant of A. So it is 16 divided by 29, right? In fact, let me go ahead and write that intermediate step there. So y is the determinant of A2 divided by the determinant of A. So we got our 16 over 29, right? And again, you can write this in as an ordered pair. You can write it as a column matrix. You can write it just the way we have here in scalar form, where you state the value of each of the variables, right? So once your coefficient matrix is invertible, in other words, the determinant of that matrix is not 0, again, Cramer's gives us a nice way of computing it, all right? So let's try a 3 by 3. Now, this will be a little bit longer because we will have more determinants, and they will be 3 by 3 determinants instead of 2 by 2 determinants. But it's important that you see that particular, this example, right? So let's say we have 2x1 plus 3x2 minus x3 is equal to 2. And then 3x1 minus 2x2 plus x3, let's say that's equal to negative 1. And then negative 5x1 minus 4, let me do that, so minus 4x2 and then plus 2x3, that's equal to 3. All right, so let's write down all the determinants that we need for this. Now we're going to need 4 determinants because you need the determinants of the coefficients, so that's 1, and then you're going to need the determinant for when I replace each of the three columns with the b's, right? Okay, so let's see how this works. So A sub A, well, just A, my coefficient matrix is 2, 3, -1, 3, -2, 1, -5, -4, 2, right? And I think what I'll do, just to keep everything consistent, I'm just going to use the cofactor expansion for each of these 3 by 3 determinants. So we'll get lots of practice with cofactors. If you wanted to use something like your row operations to turn it into something triangular, you could. But just to be consistent, I'm going to use this one method for all the determinants that we have to compute, right? So let's compute the determinant of A, and let's just make sure that it doesn't come out to be 0, right? Because if it comes out to be 0, then Cramer's rule does not apply. It means that the system does not have a unique solution. All right. So using our cofactor expansion, it's the A11, C11. So I'll write it out for this first one, and then I'll skip this step for the subsequent ones, just as a reminder of like what method I'm actually using to compute the determinants. You could even try a different method and just confirm that you get the same result. So the determinant of A is going to be 2 times, and then we have our -1 squared, and then the submatrix is -2, 1, -4, 2. So -2, 1, -4, 2, plus A12 is 3, and then that's times -1 to the third power, and the determinant of the submatrix 3, 1, -5, 2. So 3, 1, -5, 2. And then finally, our -1 times our -1 to the fourth power. And that submatrix is 3, -2, -5, -4. So 3, -2, -5, -4. All right, so let's see what we have here. We have 2 times, and then -2 plus 4, and then we have a -3 times 6 plus 5, and then we have this is also negative, right? So we have a -1 times, and then -12 minus 10, right? So let's see, so this is 2 times 2, that's 4. 11 times -3, that's -33. And then we have a positive, what's that, 22? Yeah, so plus 22. So what do we have there? Oh, wait, nope, I just saw this. Let me fix this. I need to get my eraser. This is a -4. There we go. That should be a -4. And then this is 0. So we end up with -11 for the determinant of A. So that's good. This tells me, because this determinant isn't 0, it means that the matrix has an inverse, and therefore the system has a unique solution. All right. So now let's write down, so I'm going to express the other ones just using the vertical bars. So what I'm going to write down in here is my A1. Now A1, that's when I replace the first column with the column 2, -1, 3, and then the other two columns stay the same, right? You only replace one column at a time, right? So, and I'll indicate in a second that what I have here is, so this in here is A1, and we're going to compute its determinant. And again, we're going to do the cofactor expansion, right? So I'm going to use my A11, so that's 2 times -1 squared times the minor -2, 1, -4, 2, and then plus 3, so that's my A12, times -1 squared times the minor 1, -1, 1, 3, 2, so -1, 1, 3, 2, and then finally -1 times -1 to the 4th power, this should be to the 3rd power, and then we have times our minor of -1, 2, 3, -4. So -1, -2, 3, -4. Okay, so let's compute this. We have 2 times, we have a -4, and then a minus -4, so plus 4. So that one also will be 0. And then we have a minus 3 again. And then this one is a -2 minus 3. And then this one is -1 times, and then we have 4 plus 6. Right? So let's see. So this one's 0. And we end up having, so this is -7, and then so this is a positive 21, and then this is a minus, alright, oh wait, let me fix something here. So this one, it's -2, it should be -3, right? So this should be a -3. Okay, let's get this right. So -2, and then this is -3. Here we go. So then this is going to be a positive 15, and then this is -10, and that gives us 5. Okay, so we have that one. So we have 2 of the 4 determinants that we need. Now for A2, we're going to replace the middle column, and that's going to be, so our first column will be the same, 2, 3, -5. The middle column is 2, -1, 3, and the third column stays the same, -1, 1, 2. So that matrix now is what we're calling A sub 2. And again, we need its determinant. All right, so we're going to have 2 times -1 squared. Now that minor is -1, 1, 3, 2. So -1, 1, 3, 2. And then plus 2 times -1 to the 3rd power. And that minor is 3, 1, -5, 2. So 3, 1, -5, 2. And then plus -1 to the -1 times -1 to the 4th power. And then that minor is 3, -1, -5, 3. So 3, -1, -5, 3. All right, let's see what this comes out to be. Okay, no mistakes now. So we got 2 times -2 minus 3, and then this is a -2 times, and then 6 minus -5, so that's plus 5, and then this is still -1 times, and then we have 9 minus 5, right? Okay, so this is a -5 times 2, that's -10, and then we got 11 times -2, that's -22, and then we end up having what's this? So 9, so 4, so minus 4. So this is negative 36. All right. And last one that we need, go back to our original A and now replace the third column with the 2, negative 1, 3. So this is our last determinant that we need. So we have our 2, 3, negative 5 as our first column. That's the original first column. The original second column is 3, negative 2, negative 4. And then now my new third column is the 2, negative 1, 3. And this is the A3 matrix. And we need its determinant. So once again, cofactor expansion, 2 times negative 1 squared. That minor is now negative 2, negative 1, negative 4, 3. And then plus 3 times negative 1 to the third power. And that minor is 3, negative 1, negative 5, 3. Negative 5, 3. And then plus, and then we have 2 times negative 1 to the fourth power. And then that minor is now 3, negative 2, negative 5, negative 4. Alright, so it's 2 times the quantity negative 6 minus 4 minus 3 times the quantity 9 minus 5, and then plus 2 times the quantity negative 12 minus 10. Alright, so what does that come out to be? So we got negative 10 times 2, so that's negative 20. 9 minus 5, that's 4, times negative 3, so that's negative 12. And then we have, so this is negative 22 times 2, so that's negative 44 for a negative 76. Negative 76. All right. So just as a reminder, the determinant, and yeah, let me write down the numbers now. So I'll just kind of summarize what we have, at least so we get all the relevant numbers on the screen together. So we got that the determinant of A is negative 11. The determinant of A1, that is, I can see it right there. That's, that one's 5 right there. The determinant of A2, that's right here, that's negative 36. And the determinant of A3, that's it right here, our negative 76. So Cramer says x1, the unique value for x1, is the determinant of A1 divided by the determinant of A. So that's 5 divided by negative 11, or negative 5/11. Similarly, x2 is equal to the determinant of A2 divided by, again, the determinant of A. So that's my negative 36 divided by negative 11, which is 36 over 11. And then finally, A3 is equal to, x3 is equal to the determinant of A3 divided by the determinant of A. So that's negative 76 divided by 11, right? Divided by negative 11, which is a positive 76 over 11. So here is our unique solution, right? So it provides an alternative method. So notice we didn't do any elimination at all. We obviously had to do a lot of cofactor expansion to get these four determinants that we needed, but we are able to write down the unique value for each variable using these specific fractions, right? So think of this as an alternative method. Now, if you're not required to use any particular method, then you have a choice. But if it says use Cramer's rule, then you're expected to use determinants to find the unique solution. All right? See you in the next video.